In this video, we are going to go over geometric isomers of alkenes. So geometric isomers are when two alkenes with the same chemical formula and same connectivity of atoms, so all the atoms are bonded the same, but they have a different three-dimensional orientation around the carbon-carbon double bond. The ones that we will go over are the cis-trans isomers. These are compounds that have a double bond with one hydrogen and one carbon group on both double bond carbons. So we see here, we have cis and trans 2-butene. Cis isomers are carbon groups on the same side of the double bond. So you can see here that we have a carbon group and a hydrogen on one carbon. On the other carbon, we have a carbon group and a hydrogen, and same on the other 2-butene. Cis isomer has the CH3 group or the carbon group on the same side of the double bond. They're both in the up position. Trans isomers have groups on opposite sides of the double bond. So the CH3 group is on opposite sides. One is in the up position, one is in the down position. So trans is opposite, cis is the same. And these compounds are named by assigning the name as before. So naming the alkane via normal IUPAC rules, but adding cis or trans followed by a hyphen to the beginning of the name. This indicates whether the orientation around the double bond. So saturated and unsaturated fats. Unsaturated fats have cis double bonds. So you can see here, this shows you, this doesn't show you the H's, remember, but these are carbon groups on both sides and hydrogens on the other side. The hydrogens are on the same side, the carbon groups are on the same side, therefore they're cis bonds. Same here, we have hydrogens on both sides, carbon groups on the same side on the other side. They're cis bonds. The cis geometry creates a bend in the chain. You can see that it goes to zigzag conformation and then it goes to a bend and then it continues on. Saturated fats stack up well, leading to stronger dispersion forces and higher melting points than unsaturated fats, because you can see in a saturated fat, there's no double bond there and there's no opportunity for that cis bond to become there and create that kink. So it stacks up really well, and that's when you get the higher melting points than unsaturated fat. A higher melting point would be like butter versus an oil. So practice, we're going to label these pairs of compounds as cis isomers or trans isomers or the same compound. So take a look at these, pause the video, and then when you're ready, come back. Okay, so the first thing we're going to do is, in order for you to have a cis or trans isomer, you need a double bond. These first two have a double bond. So we're going to look at the double bond only, and we're going to write our hydrogens in. We have hydrogens on both sides on the top, and carbon groups on the bottom on this first one. So this means it's cis. So cis is the same side. Trans, we have a hydrogen on top, a hydrogen on bottom, and we have the carbon groups on opposite sides as well. So this is trans. All the other, it has the same molecular formula. So it's the same compound. The only difference is the orientation around this bond, the 3D orientation. So these are cis-trans isomers. So cis-trans isomers. Here, we look at it and there's no double bond. So these aren't cis-trans isomers. They're just the same compound. You need to have a double bond in order to have these cis-trans isomers. So in summary, carbon-carbon double bonds cannot freely rotate like carbon-carbon single bonds, but so that's how you get those conformational isomers. So we only have the cis-trans isomers or or we have other isomers, but we have the geometric isomers in carbon-carbon double bonds. And that's when there are two different atoms or groups on both double bonded carbons. The cis-trans isomers are a type of geometric isomers that have a hydrogen and an R group on both double bonded carbons. The cis isomer has both R groups or both H groups, whichever way you want to look at it, on the same side of the double bond, and the trans isomers have groups on opposite sides of the double bond.